Hi class, in this video we are going to continue a few examples for the calculations of pH value for weak acid and weak base. So let's look at question number 3 first. The table below lists the value of acid dissociation constant Ka for some acid at 298 Kelvin. Arrange the acid in descending order of the acidic strength. So descending order, it means that you need to arrange starting from the most acidic towards the least acidic. So you need to remember that the higher the Ka value, it means that this weak acid will dissociate more to produce the H+. So higher the values of Ka, the stronger is the acid. Now, stronger the acid. So in this case, you need to arrange according to this Ka value. So we're starting with the strongest acid among three of this acid given. And then you look at the highest value of Ka, which is this one. Okay, so it refers to HNO2. So starting for the highest Ka value, which means the most acidic. Okay, you may also want to jot down over here, we will start with the most acidic acid. Okay, so it has the highest value of Ka, which refer to HNO2. The second highest goes to CH3COOH. And the third one, or the least acidic, which has the lowest value of Ka, goes for the HCN. So HCN in this case is the least acidic. If you want to do some explanation, you may explain that HNO2 is the most acidic as it has the highest Ka value. So according to this question number 3, madam, add one more question. If the questions ask you to arrange the strength of conjugate base for the acid given above in ascending order, okay, or the increasing orders, starting from the weakest to the strongest. So before you arrange into the order, you need to figure out what is the conjugate base for each of the acid mentioned here. Okay, so let's look at your HNO2. So remember that these are all acid. An acid will donate proton. After it donates the proton, it becomes conjugate base. Okay, so HNO2, after releasing one proton, H+, it becomes NO2 negative. Okay, so on the top over here, you have your weak acid, and the bottom over here is the product of your conjugate base. Okay, so I've just listed out over here. And then the conjugate base for CH3COOH, after you releasing one proton, it becomes CH3COO negative. And then HCN, after removing a proton, becoming CN negative. So these are all the conjugate base. All right, so you need to remember this one. Okay, this one you can find out from your notes. Okay, so the stronger the acid, so the weaker is conjugate base. Or vice versa, the weaker the acid, the stronger is its conjugate base. So I'm using a different color. So HNO2 is the most acidic one, or it is a stronger acid. Okay, so on the other side, it means that the conjugate base is the weakest, or the least basic. The stronger the acid of HNO2, the weakest is the conjugate base NO2 negative. Whereas if you have the least acidic HCN, that is the weakest acid. Therefore, the conjugate base CN minus is the strongest. So we want to arrange in the ascending order. We start with weakest and then slowly go into the strongest. Therefore, NO2 negative is the weakest, followed by CH3COO negative, and then the strongest conjugate base goes to CN minus. So using the same concept, you may try question number 1 and 2 in your exercise. Next, we have our question number 4. So given over here, you have your pKb value, which is 4.70. Calculate the concentrations of OH minus ion in 2.0 molar of ammonia solutions. Again, a weak base. So in this case, you need to convert this pKb value into Kb. So applying the formula pKb equals to negative log Kb. So you have 4.70 for pKb value, negative log Kb. So rearrange that to get a shift log. Okay, don't forget to bring over this negative sign towards the 4.7 here. So we have 10 to the power of negative 4.70, or the shift log negative 4.7. And you will get the value of pKb equals to 1.995 times 10 to the power of negative 5. There's no unit for Ka or Kb. So now you have your Kb value for this ammonia solution. So you have to come up with the equation for this partial dissociation. Because it is a weak base, so it has the partial dissociation. So NH3 aqueous solution dissolved in water, liquid, is in equilibrium to produce the conjugate acid. Again, why is it conjugate acid? Because NH3 is the weak base. Okay, so NH4 positive, this will be your conjugate acid. All right, and plus OH minus after the water releasing the proton. So you can draw a ice table. Okay, so over here, madam didn't draw the ice table. Yeah, you need to, if you want to, you may do so. So we have the initial concentration, we have the change in concentration, and we have the equilibrium concentration. So initial concentrations for ammonia given is 2.0. Okay, constant concentration for H2O, so you don't have to fill in anything over here. And then initial concentration for this conjugate acid is 0. OH minus also 0. So NH3, the change in concentrations minus X, NH4 plus X, OH minus plus X. And the equilibrium concentrations, we have 2.0 minus X for the ammonia, and then X for NH4 plus and X for OH minus. Okay, so we want to come up with the Kb expressions. Again, it's the same thing. Okay, your Kb expression. Substitute the values that you have found out from the Kb values or from the ice table. So remember that from the ice table, we'll take the final column over here to do substitution. So 1.995 times 10 to the power of negative 5 equals to x squared because x times x. And then over concentrations of ammonia, 2.0 minus x. And then solving your quadratic equation. You may want to check whether you got the same quadratic equation as this or not. So after that, figure out the value of the x. You will get two values of x, then we choose the one which will give you a positive concentrations. So in this case, the x value is 6.3 times 10 to the power of negative 3 molar. Okay, so go back to the questions again. The questions ask to calculate the concentrations of OH minus in the solution. So over here, you're referring to your ice table. We want the concentrations of OH minus. Therefore, it is the value of X. You may write like this. Okay, so here is the answer for your questions 4. Question number 5. Butyric acid C3H7COOH is used to make compound employed in artificial flavoring and syrups. A 0.250 aqueous solution of the acid is found to have a pH value of 2.72. Determine the Ka for butyric acid. So first of all, you need to convert this pH value. Okay, if the pH value is given, that means it has already given you the information of the concentrations of H+. Okay, so the pH formula, pH equals to negative log concentrations H+ or H3O+, which is equals to 2.72. Therefore, the concentrations of H+ equals to shift log negative 2.72. And the values of the concentrations equals to 1.91 times 10 to the power of negative 3 molar. Please practice using the shift log in your calculator. You need to familiarize how to do in either way, whether you want to do negative log concentration or you want to shift log the pH value. Okay, so practice using calculator. If you have any problem, you need to ask for help. Right, so now we have got our concentrations for H+. The next thing what you want to do is to construct an ice table. Right, so we have the butyric acid C3H7COOH aqueous solution, and then in equilibrium it will dissociate to give the conjugate base, or an acid dissociate to give conjugate base, and the H. So initial concentration 0.250, 0 and 0 for the product. So the change in concentrations according to your balance equation, minus X for reactant plus X for the product. Then the equilibrium concentration, we have 0.20 minus X, X and X. So the working step is quite similar. The ice table is quite similar. Okay, for all the example, what you need to do is just to reconstruct, refill in the informations following each of the questions. So in this case, the concentrations of H plus is equals to the X. So where did you find that? So H plus is the same as the value X. So equals to 1.91 10 to the power of negative 3 molar. So constructing your Ka expression. So we have Ka. A little bit of corrections over here. This one is C3H7. Okay, so Ka expressions, you have this conjugate base on the top and then H plus on the top, and then on the bottom you have the weak acid COOH. So X times X over 0.250 minus X. So since the value of X we have already calculated, so we just fill in the blank. So 1.91 times 10 to the power of negative 3. Since you have 2x, we just raise to the x. Or if you want to write straight away x squared, also can. Alright, so 0.250 minus the value of x. And you will get the answer equals to 1.47 10 to the power of negative 5. Again, K constant doesn't have any unit. So this is the overall answer for our questions 5. So the working step is quite similar depending on how the questions give you information. So anyway, if you have the weak acid or weak base, you need to refer to the ice table. Okay, in order to get the informations of concentrations to substitute into your Ka expression or Kb expression.